Good day. You're welcome to this episode of our lecture. Um, Today we are going to look at the quantum theory of an atom. We have looked at the classical description of an atom, where atoms are considered, electrons are considered to be in energy level. Today we are going to look at the quantum nature of an atom. Now, so many people, scientists have performed experiments in which it is pretty difficult to determine the position and the momentum of an electron at the same time. So they now came up with the picture of an orbital, and it is considered that instead of looking at an electron to occupy a shell, but electron is now considered to occupy an orbital, which is a region in space with the maximum probability of finding an electron. People like Louis de Broglie observed that since light is said to behave like a particle and a wave, therefore electron is also, which is a subatomic particle, is said to have a dual nature. That is, it has a particulate nature and a wave-like nature. And he succeeded in proposing an equation whereby he calculates, since if you are talking of wave, then a wave must also have properties of all waves. He succeeded in calculating the lambda, which is the wavelength of light, and at the same time, he succeeded in calculating the momentum through this is famous equation. You can see the lambda, the h is the Planck constant, and p is the momentum, which is equals to mass times velocity of electron. Heisenberg, one of the other scientists that contributed, is the German physicist known as Werner Heisenberg. He stated that it is not possible, like I said earlier on, it is not possible to determine accurately the position and the momentum of a particle within a certain limit of accuracy and they try to justify this through his mathematical expression, which is delta S times delta P is equal or greater than h over 4 pi, where x is the uncertainty in position, delta S, that is change in x, is the uncertainty in position of the particle, and delta P is also the uncertainty in momentum of the particle. Nature of light. Light was initially thought to be made up of a stream of particles, courtesy of Newtonian corpuscular theory. This assumption can explain phenomena such as reflection and refraction. But however, there are some other phenomena that this corpuscular theory cannot explain. Such phenomena are issues of interference and diffraction. But this case is being taken care of through the view of people like Maxwell in 1956, who attributed the wave-like nature of light instead of the corpuscular theory of light proposed by Isaac Newton. Light wave was also known to be electromagnetic in nature, hence it carried other properties of a wave, such as the frequency, the wavelength, and the rest. Another property of light is that it has quantum nature, which means light energy is carried in packets named as photons. Albert Einstein proposed an equation showing the relationship between the energy and frequency of light, which is energy of light, which is E, is equal to h over frequency, where h is the Planck constant with value of 6.63 times 10 raised to the power minus 34 joules, and V is equal to frequency. So, orbital theory and quantum number. From Heisenberg uncertainty principle, which state the impossibility of determining accurately the position and momentum of an electron. This implies that electron can be visualized to be in space. And in 1926, Ernest Schrödinger proposes his own equation describing the three-dimensional standing wave by imposing wavelength restrictions suggested by the Broglie experiment. And the equation allowed him to calculate the energy level in the hydrogen atom. However, modern technology has made it possible to use the equation to solve more complex systems from hydrogen atom. So the solution to this Schrödinger equation give a set of three kind of number known as quantum numbers that describe L, that describe one, the energy of the electron in an atom, two, the shape, and three, the orientation of the orbital. In 1928, Paul Dirac reformulated electron quantum mechanics to take into account the effect of relativity, which gave rise to the fourth quantum number, that is the spin quantum number. Altogether, we have four quantum numbers: the principal quantum number, the azimuthal quantum number, the Sommerfeld, the magnetic, and the spin quantum number. Now, the solution of the Schrödinger and Dirac equation for hydrogen gave four quantum numbers, like I earlier said, that describe the various states, energy states, available to hydrogen single electron. We can also use this quantum number to describe the electronic configuration, that is, the arrangement of an electron in all atoms. The principal quantum number n describes the energy level an electron occupies. It has an integral value of n is equals to 1, 2, 3. We have our azimuthal, or the subsidiary, or the Sommerfeld quantum number, designated as small n, and its value ranges from 0 up to n minus 1. That is, it can be 0, 1, or 2, and so on. The first shell, or K shell, have only one subshell with value of L is equals to 0. The second shell will have two subshells, is L equals to 0 and L is equals to 1. The third shell will have three subshells, which is L is equals to 0, L is equals to 1, and L is equals to 2. The value of L is equals to 0 is equivalent to S. When L is equals to 1, it's equivalent to P. When L is equals to 2, it's equivalent to D. And when L is equals to 3, it is equivalent to F. This is what gave rise to our S, P, D, and F orbitals. The magnetic quantum number describes the spatial orientation of atomic orbital. It can have integral value of -1 to 0 and +1. So if the M has a total value of 2L plus 1, it gives an S subshell which is L is equals to 0, there's one orbital. In the case of P subshell, which is 1, we can have three orbitals corresponding to three values of -1, 0, 1, and +1. And the three orbitals are represented as Px, Py, Pz. And when L is equals to 2, the orbital is equals to 2 times 2 plus 1, which is equals to 5. This means that we have 5d orbital corresponding to -2, -1, 0, +1, +2, altogether making up 5. And at the same time, for F orbital, we have our -3, -2, -1, 0, +1, +2, +3, making up to 7 orbitals, 7 different orbitals. The spin quantum number gives the spin of the electron. This is either described as either it is clockwise or it is anti-clockwise, and it can be represented as +½ or -½ Let us look at rules governing filling of an electron in an orbital. We have our Akhbar rule. It states that electrons are added progressively to the various orbitals in the order of their increasing energy, starting with the orbitals of lowest energy. Then the second principle is that of Pauli. Pauli said the sequence of filling an orbital or writing an electronic is as follows: 1s, 2s, plus 2p, 2p plus before 3s, 3p before 4s, and so on as so forth as shown on the screen here. Thank you for listening, and we wish you key in to our next lecture.